with another video. Today I am going to discuss with you the electrophilic addition to alkenes, as you have just seen on the board. In my previous lecture, I have explained you briefly the addition, elimination and substitution reactions. So today let's discuss this very interesting topic called electrophilic addition to alkenes, that is carbon-carbon double bonds. I am Professor Dr.Mchem from Dr.Mchem Institute of Chemistry, University of St. Jamshoro, and I welcome you all to my channel. Let's discuss this awesome topic. Addition is the commonest it is the commonest of all the reactions, you can say of all reactions referring to alkenes, right? Referring to alkenes. Which type of reactions? The addition reactions is the most commonest of all the reactions if you are talking about the or you are referring to alkenes. Now what happens on adding, you can say on adding number of reagents. I hope everyone knows what is a reagent. You are a chemistry people. You know what are reagents. So now what happens on adding number of reagents? Now on adding number of reagents to a double bond, right? To a double bond, of course, what of alkenes? We are talking about, we are discussing alkenes today. Results in what? Forming different functional groups. Right? What it results in? Forming different functional groups. Different functional groups, right? What happens? What I just explained, that is first of all, addition is the commonest of all the reactions referring to alkenes, which is our topic as we are discussing electrophilic addition reaction to alkenes. So now what happens on adding number of reagents to a double bond, that is this one, right? A double bond, that is alkene double bond. It results in forming different functional groups. So as you know that a number of reagents, wide number of reagents, a wide number of reagents can be added to, of course, this alkene, right? Alkene's double bond, right? Double bond, what it would resulting most of the stable products, right? Stable products. And such reactions are favorable, how? Energetically. And such type of reactions are very much favorable energetically, or you can call them energetically favorable reactions. That is when you will add a number of reagents to an alkene double bond, what it will form, of course, the most stable products. But of course they do not have suitable rates. Now what are rates? Of course the rates of reaction we are talking about, not the rates of the products you are finding in shopping malls. No, the suitable rate, that is the speed of reaction, the rates of reaction. And sometimes rate is very slow, like reacting ethylene with hydrogen, right? I will show you now in my next slide. So sometimes the rate is very slow, okay? It is very slow, like you can say reacting when you are reacting what? Reacting this ethylene C2H4, that is this one, ETHYLENE, ethylene, with some hydrogen you can take, right? With hydrogens, with some hydrogen, forming what? Of course, it's a simple example, ethane, forming ethane. And is a powerful, but this is a very powerful what? Exothermic reaction. Thermic reaction. Now, what is an exothermic reaction? I hope everyone knows what is an exothermic reaction. What is an endothermic reaction? So to run a reaction at a rapid rate, addition of a catalyst like platinum, nickel, palladium is always needed, always a must, right? So to run a reaction, what type of platinum, or you can say to run a reaction at a rapid rate, you need to add some catalysts, right? And what type of catalyst? I will show it with a different color. Platinum, nickel, nickel, and of course palladium are the good examples. Palladium is a must, right? So now there are reagents that do not require any catalyst to react with these carbon-carbon to carbon-to-carbon double bonds. There are a few reagents which do not need any catalyst to react with this carbon-to-carbon double bond, right? And to follow the types of the reagents that can react with carbon-to-carbon double bond, you must follow first. What is this pi bond? What is the pi bond? What is a pi bond, right? Or the structure of a pi bond. So let's draw a simple structure of a pi bond between, of course, a little bit lower, like this, right? Okay, and a carbon over here. Carbon, right? These are the two carbons, and I'm not going to draw a pi bond between them. Okay, so this is, of course, something else. I will tell you what it is. It's very easy. I mean, these are the dashed, and this is a solid wedge. Now, as you know, I have shown you, I have made you learn a lot of stereochemistry too. So you must be knowing why I'm drawing this formula, like with this solid edge and a dashed bond and a solid bond and a dashed bond, right? And okay, so now I use a different pen so that I can show you a sigma bond between this. This is a sigma bond. And this sigma bond is closely, C-L-O-S-L-Y, close, sometimes I forget the spellings, closely held together. This sigma bond is closely held. Whereas this is what? Half of the, what? Which bond? Pi bond. Pi bond. This is half of the pi bond. And this is another half of the pi bond. Half of pi bond, right? And these are the, you can say, the two pi bonds, right? And this is the sigma bond, which is closely held. Now this figure simply illustrates a pi bond with the electrons, right, to be seen away from the carbon nuclei, the electrons that are away from the carbon nuclei and are loosely held, right, loosely held. Then the sigma bond, then this sigma bond, these are away and they are not that close, whereas this one is, I mean, you simply see here that it simply explains us that pi bond electrons to be seen very much away from the carbon nuclei, whereas and are loosely held than these sigma electrons, which are very, I mean, strongly holding each other together. So sigma bond electrons are very close enough. Here now what is happening? These sigma electrons, sigma bond electrons are close enough. This is what I'm writing, and hold tightly. I'm writing it for those who ask me to be a little bit slower in explaining. So T-I-G-H-T-L-Y. See, I'm again forgetting the spellings of the simplest words. Okay, so now here I'm just explaining this figure, that is the structure of a pi bond, right? What it is like, right? So here just I'm explaining that sigma bond electrons are close enough and hold tightly as compared to the what? As compared to the pi bond, right? A pi bond, that is this one, pi bond, which is delocalized, above and below. That is above and below. This is delocalized. This is the delocalized forms. Delocalized above and below, B-E-L-O-W, below the sigma bond, right? The sigma bond, as you can see in the figure. What is this is happening here? It's very simple. This is a simple concept which you might have been told by many teachers of your institute. Many times you have heard, but you know, still students are coming up with this assumptions that we can't understand the additions to carbon-carbon double bond and we cannot follow our teacher properly. So let us explain it on the board. So that's why I'm explaining all this stuff on the board, so that it would be a bit easier for those students who are a bit weaker in following this topic. So it's not for those who have the expertise. Don't consider yourself only. We are considering the students who are you know, getting the points a little bit slower than the bright ones, the ones who are the highlighted students. So please have mercy on the others. Okay, so this is simply I explained you, as you can see in the figure, right, that these sigma bond electrons are close enough and hold tightly, whereas then the pi bond delocalized above and below the sigma bonds, right? So this is what is happening here. Now here what happens, that as you see, this is what is happening in the figure. This is what I've explained. Now what happens, that at this situation, an electrophile, which is, you know, electrophile means electron loving, has an affection for these electrons that are loosely held, right? That are loosely held. They have this electrophile has an affection for these electrons that are loosely held, right? So let's discuss them now. So here now you can simply see I have drawn this, I've written all this. An electrophile, I just told you, it has an affection, right? It has an affection. You can see its smiling face, right? You can say a face that is saying that I'm going to snatch away your electrons. So it has a great affection for the electrons that are loosely held. In that previous figure, I've told you that the electrons on that pi bond were loosely held together. So for those loosely held electrons, it holds the affection, the electrophile, this one, right? And now as they were loosely held and can be snatched, they can be pulled, snatch them away from forming what happens when it snatched it away, it will form a new bond, right? As in the figure below. Here you can see in the figure, I can show you what is happening in the figure. Simply see in the figure, the electrophile, right? It is now trying its level best to snatch away these electrons, this powerful electrophile. It is going to snatch away these loosely held electrons, right? Forming a new bond. Now, if I proceed here with the reaction, I will show you what happens. What will happen now here, I'm going to show you the carbons, right? The same two carbons over here. Okay, now I will show you something else. The empty p orbitals, which is empty. how it becomes empty, I'll show you. As what this will happen here after the snatching of the electrons, same dashed bond, wedged bond. Okay, what happens, you will have and when the electrons will be, as the electrons are pulled away by this electrophile, right? The double bond, actually what happens, the double bond, this double bond, it acts as a nucleophile, right? This double bond, it acts as a nucleophile, resulting, forming this as a carbocation. Because one of its carbons is snatched, right, from the double bond, right? One of its, what is happening here, as the electrons are pulled away by this electrophile, and this double bond, you know, this double bond, it acts as a nucleophile. This acts as a nucleophile that gave its electron pair to that electrophile. It gave its electron pair to this electrophile, right? Now what will happen, leaving one of the carbons, that is one of these carbons with the 3 bonds only, that is this one with the 3 bonds and a positive charge, 3 bonds and a positive charge, that is a carbocation. Now what is this? This is a carbocation. This is a carbocation. Somebody can ask you, what is a carbocation? So this is a carbocation. This carbon is called a carbocation. Now this curved arrow, this one, it exhibits electron movement from a pi bond, that is from this pi bond that was rich in electrons, to the electron poor electrophile, right? What is happening? The electrons are moving towards the electron poor electrophile and forming a carbocation. Here you can see a carbocation with a carbon that has got a p orbital, which is empty. So this happens here. I have explained the reaction here. These electrons are pulled away by this electrophile, which was here, right? You can see this electrophile, because this pi bond was acting as a nucleophile, that it gave its electron pair to the, this electrophile, right? It gave its electron to its electrophile, leaving one of the carbons with the 3 bonds and a positive charge, that is a carbocation. It's a carbocation and a positive charge, that is a carbocation, right? And these electrons, you can see here, they have been, they just joined there, and it becomes another new bond, right? Now here many of the addition reactions, they proceed further. Now here the reaction is not stopped. They proceed further by a second step in which carbocation, that is this one, is attacked by what? By a nucleophile. This carbocation will be attacked by a nucleophile, just like in the second step of the which reaction? The SN1 reaction. If you have read the SN1 reaction, in that reaction also, in the second step of that reaction, the same thing happens, that this carbocation is attacked by a nucleophile, right? So now, as I was just mentioning to you, many addition reactions, there are many addition reactions which proceed further by the second step, right? The second step. What is the second step? In which the carbocation itself is, it is attacked by a nucleophile, right? Just like in the second step of SN1, that is the results in forming a very stable addition product, right? In which both electrophile and nucleophile bonds to the carbons of the double bond, as shown in this figure. You can see here, this is what is happening here. Attacking of a pi bond on the electrophile, right? Pi bond on the electrophile. Now it is attacked by an electrophile, forming, of course, this one, right? A carbocation, and a carbocation, which is a strong electrophile. A strong electrophile attacks loosely held pi bond electrons of this alkene, right? What happens? That this attack on this pi bond by this electrophile, it forms a carbocation here. Formation of a carbocation, right? Again, a formation of a carbocation. As the strong electrophile, right, it attacks loosely held, the loosely held pi bond electrons of that alkene, right? This alkene. Because as I've mentioned in my previous figure, you have seen that they were loosely held. They are loosely held. So the electrophile forms a which bond? A sigma bond. a sigma bond. Which one with one of the carbons of the alkenes carbon of the double bond, right? What happens where it is forming like this electrophile? It forms a sigma bond, right, with one of the pair, with one of the carbons of the alkenes of this double bond, right, and becomes a carbocation. It becomes a carbocation, which is a strong electrophile, and with this one is able to react with a nucleophile again to form a sigma bond, as shown in this figure. I can show you here again. This is this electrophile, right? What is this now doing? It is attacked by this again, the nucleophile, right? This is a nucleophile. Now what happens that it attacks again this carbocation, right? And what happens here? It forms a product in which the electrophile gets itself attached over here, and this nucleophile, it gets attached here, just like here. You can see here. So this is what is happening. That is, the electrophile forms a sigma bond with one of the carbons of the alkenes right here and becomes a carbocation, which is a strong electrophile and which is able to react with a nucleophile, within this nucleophile to form a sigma bond, as shown below here. You can see it is again forming a sigma bond. Here you can see here that this carbocation is attacked by this nucleophile, right, and a sigma bond formation took place. And this attack of a nucleophile, nucleophile gives what? Results into an addition product. Which was our goal, to get the addition product. It gave us the addition product. This attack of a nucleophile, it results giving us back the addition product. So this was a detailed topic regarding this addition reaction of alkenes. I hope you have learned and you have enjoyed now that what is happening here and how all this process it goes on. What is the role of the sigma bond electrons in it, and why they are close enough, and why they hold tightly as compared to the pi bond, which is delocalized above and below the sigma bond, as I've shown, as I tried to explain you first what is a pi bond, because most of the students don't understand what is a pi bond. So I explained the pi bond also, and then in the beginning I told you what is electrophilic addition to alkenes. And I told you that then there are a number of reagents that can be added to alkene double bond, resulting most stable products. We can get the stable most products, and such reactions are very much favorable. That is, they are energetically favorable. So I hope you like this video and you will compare it with your notes to addition of carbon-carbon double bonds, addition of alkenes to carbon-carbon double bonds, and it would be useful for all my students who are going through these topics right now, and it would be provide a little bit knowledge to them. So compare it with your literature provided to you by your teacher, and try to learn, try to learn the reaction, how it goes on, how all the steps they simply progress with the reaction. So hope to meet you again with the continuation of this topic further, and I will give you another example also of addition of this alkene to carbon-carbon double bond with some other examples also. So let's meet again. Thank you very much.